In this lesson, we're going to look at higher order derivatives. Okay, so you should probably realize that just like any other function in math, a derivative can be applied to an expression or a function multiple times. Just like you could take the square root of 16 and get 4, and then you could take the square root of 4 and get 2, and you could continually take the square root of your answer as many times as you wanted to. We can do the same thing with the derivative. You can take the derivative of a function and get an answer, and then you can take the derivative of that answer, and you could keep repeating this process continually. Okay, if you take the derivative of a function twice, it's called the second derivative. Okay, so here are some notations for second derivative. Okay, so for instance, if we had the function 5x cubed minus 13x, and we wanted to take the first derivative, or the derivative, we'd get 15x squared minus 13. If I want to take the derivative of the derivative, or the second derivative of the original function, we'll notate that with 2 prime marks, indicating that we're going to take the derivative twice. And then all I do is I take the derivative of the derivative. So we use the power rule here, and 2 times 15 is 30. That becomes 30x. The derivative of negative 13 is 0. So the second derivative would be 30x. You could continue. You could take third derivative. If I take the third derivative, I take the derivative of the second derivative, and it would just be 30. Okay, and you could do this as many times as you needed to. You know, if you were asked for higher order derivatives, you just continue the process. Okay, so in this section, we're mainly going to look at the second derivative. Okay, now notice here's the notation I used a second ago. You know, we could also use y double prime, which means the same thing. But this notation for the second derivative looks a little bit different than what you might expect it to be. Okay, but remember how I told you that when you see something like dy dx, you should think of it as taking the derivative, the d dx, meaning take the derivative of the y that comes after it. So this part right here means take the derivative, and we're taking the derivative of y. We just shorten it, or kind of condense the notation, and write it like this, dy dx. So if I want to take the derivative a second time, we indicate that in this notation with what looks like a squared. Okay, so this would be take the derivative twice of whatever comes after it, but we don't really write it like that. We go ahead and condense it like we did before, and then this would be the d, it looks like d squared y, and it looks like dx squared, but it really means just take the second derivative of y with respect to x. Okay, so that's pretty much just notation. If you want to pause the video for a second and try these two on your own and then check the answers, I'm going to go ahead and work them out. Okay, so the first derivative for this one would be 10x. The derivative of sine is cosine, and so it would be 10x cosine plus cosine x. The second derivative is the derivative of this. Derivative of 10x is 10. The derivative of cosine of x is negative sine x, so it would be 10x minus sine x. Remember, if you forget which one should be positive or negative, I told you can write it out like this. The derivative of sine is cosine, but the derivative of cosine is negative sine. All right, for the next one, it says find the second derivative at pi over 4. So first we need to find the second derivative, and before you can find the second derivative, you need to find the first derivative. Okay, so the derivative of sine is cosine. The derivative of cosine is negative sine. And we need the second derivative at pi over 4. So that's going to be negative sine of pi over 4. Well, the sine of pi over 4 is the square root of 2 over 2, but it's calling for negative sine of pi over 4, so it's negative square root of 2 over 2. Okay, so this is just a quick review of the previous lesson. If we have a particle that's moving in a straight line, it's saying that its position can be given by this function right here, t cubed minus 6t squared. where S, the position, is measured in meters, and T, the time, is measured in seconds. And we want to find the instantaneous velocity at t equals 4. Okay, so if you want to pause the video and try it before I work it out, you can do that right now. Okay, the velocity is the derivative of position. So in this case, it would be 3t squared minus 12t. We need the velocity at t equals 4, so I'm just going to plug this in to the velocity function, and then we could just work this out from here. So we get 3 times 16 minus 48. Well, 3 times 16 is 48, and so this would just be 0. And if we had units, it would be in meters per second. Okay, so velocity is the rate at which position changes with respect to time. And notice that our units kind of emphasize that. The units for velocity in this case are meters per second. It is the rate of change of distance or position, in this case position, which would be measured in meters with respect to time over seconds, meters per second. So what would the rate at which velocity changes with respect to time be called? Okay, well, the rate at which velocity changes with respect to time is acceleration. Okay, so we need some notation here. We already know that x of t or s of t will give an object's position. If we take the derivative of the position, we get velocity, and actually if we take the derivative of velocity, we get acceleration, or the second derivative of position will give us acceleration. Okay, so I always like to think about units here. Our position function, which we could also write dx dt. No, we couldn't. We just write it x, sorry. I'm ahead of myself. Which we just write in like x of t or just x might be measured in meters. If I take the derivative of this, I get velocity, and I could write this as dx dt. Our x up here would be in meters, and our time might be in seconds. If I take the second derivative of position, or the derivative of velocity, or acceleration, I take the derivative of this thing up here with respect to time, which would look like this. And so I've taken the derivative with respect to time twice, so the top is still my position meters, but I've taken the derivative with respect to time twice, and so the units here would be meters per second squared, or meters per second. So if our original position function is in meters, velocity might be in meters per second, then acceleration would be in meters per second squared. If this were in miles, this one might be in miles per hour, and then this one acceleration would be in miles per hour squared. So you can use the units to kind of help you figure out which one is the derivative of which. All right, so let's look at this one. This is the same one we did a second ago. We had the position function, I think it's the same one, yeah, as t cubed minus 6t squared. The velocity was the derivative of that, which was 3t squared minus 12t. And if we want to find the acceleration of the object at t equals 4, we just take the derivative of velocity. So that would be 6t minus 12. And if I want the acceleration at t equals 4, I just plug it into the acceleration. I get 24 minus 12, or 12, and the units would be in meters per second squared. Okay, so here I have a table for a position function, t cubed minus 6t squared, and I just kind of wanted you to go through and see if you could find the position, the velocity, the speed, and the acceleration at each one of these times. Okay, now if you want to pause it and try it yourself, you can. I'm just going to kind of uncover these and talk through it. If I wanted to find the position at any given time, I just plug these values into this up here. So if I plug in 1, I get 1 cubed, which is 1, minus 6 times 1 squared, so it's going to be 1 minus 6, and so that would be negative 5. I could plug in 2, and you should get negative 16. And remember that this is just giving me the position. Where is it on the number line at any given time? Okay, to get the velocity at any given time, I'd take the derivative of position. So I'd get 3t squared minus 12t, and then I would do the same thing, but now I'd be plugging these times into the velocity. So if I plug in 1, I get 3 minus 12, or negative 9. If I plug in 2, I'm going to get negative 12, and you can try each of these. If I plug in negative 9, if I plug in 3, I get negative 9. If you plug in 4, you actually get 0. And each of these would be the velocity, the instantaneous velocity at any given time. Okay, now remember we said speed is the absolute value of velocity. So all I need to do is look up here at the row above it and make everything positive. Okay, so remember speed is always positive, velocity could be positive or negative because it indicates direction. In other words, right here, the object's moving to the left because velocity is negative, but over here at the end it's moving to the right because velocity is positive. However, speed is always positive. Okay, to find the last row, I'd find the acceleration, so I would take the derivative of velocity, 6t minus 12, and then I'd plug these times in to the acceleration function. If you plug in 1, you get 6 minus 12, or negative 6. If I plug in 2, I get 12 minus 12, or 0, and we could keep plugging those in, and then I could get the acceleration at any given time. Okay, so we're going to use this table to kind of talk about what's happening to the object at different times based off of the velocity and acceleration. Okay, so one thing you need to realize is that if the velocity changes signs from positive to negative or negative to positive, the object changes direction. And this can only occur when the velocity is equal to 0. So velocity can't go from positive to negative unless it passes 0 along the way. You could have an object that's moving to the left with a negative velocity. If it's going to start moving to the right, first it has to come to a stop for just an instant where the velocity is 0, and then it can start moving to the right. Okay, but here's something you probably want to write down. This is important. It shows up a lot on the AP exam. If velocity and acceleration have the same sign, the object is speeding up. Okay, if velocity and acceleration have different signs, the object is slowing down. So in other words, if they're both positive, the object's speeding up. If they're both negative, the object's speeding up. If you have one of each, positive and a negative, or a negative and a positive, then the object's slowing down. Because acceleration is a force that works against velocity. So you imagine you've got this guy, okay, I'm no artist, and he's walking this way. Okay, and imagine that, okay, so he's walking to the right, so velocity is going to be positive. Okay, and imagine that there's a force like wind or something like that that's blowing this way. Okay, and that's going to be like our acceleration. It's the force against him. And since it's going, the wind is blowing to the left and pushing against him, we would think of it as like acceleration being negative. Well, if he's walking to the right and this force is continually pushing towards the left, he's going to be slowing down. Okay, but on the flip side of that, if he's walking to the left and he has a negative velocity and the wind is blowing behind him, or someone comes up behind him and pushes him from this side towards the left, velocity and acceleration will both be negative, and he's going to be speeding up going towards the left because he's walking to the left, and the force of acceleration, whether it be someone pushing him or wind blowing or whatever it is going to cause him to speed up because they're going in the same direction. So if velocity and acceleration have the same signs, whether they both be positive or both be negative, the object's speeding up. Okay, so acceleration, just like velocity, if acceleration is positive, that means the force of acceleration is pushing either to the right or up. If acceleration is negative, the force of acceleration is either pushing to the left or down. If you know anything about gravity, gravity has negative acceleration. Gravity pushes objects down. If an object is falling, if you drop it, okay, so its velocity is going this way, you drop it, acceleration due to gravity, acceleration is also negative, going down the same direction, the object's going to speed up. But if you throw the object up, gravity is pulling it down, acceleration due to gravity is negative, the velocity of the object is positive because you threw it up, they have opposite signs, the object will actually slow down. until it turns around and goes the other direction. Okay, so this is how we justify whether or not an object is speeding up or slowing down. We have to find the acceleration and the velocity and see if they have the same sign or different signs. Okay, so we're going to look at this table right here and see if we can figure out what's happening at each of these times. All we need to do to figure out direction of the motion, left or right, would be to look at the velocity. Okay, so if the velocity is negative, it's moving to the left. The velocity is negative, it's moving to the left. Velocity is negative, it's moving to the left. If velocity is 0, it's not moving. And if velocity is positive, it's moving to the right. But now we want to know if the particle's speeding up, slowing down, or neither. So we have to look at velocity and acceleration. So at t equals 1, both velocity and acceleration are negative, so the object's moving to the left and it is speeding up. Because they have the same sign, velocity and acceleration are both negative. Okay, and so at t equals 2, you can see that the velocity is negative, so the object's moving to the left, okay, but acceleration is 0. So that means the object is not speeding up or slowing down, it's moving at a constant velocity, and so this one would be neither. Okay, at this time, the velocity is negative, but acceleration is positive. So the object's moving to the left, but acceleration is pushing it towards the right. And so since these have opposite signs, one's negative and one's positive, the object would be slowing down. Okay, the object's not moving at this time. Well, if the object's not moving, they're not going to ask you this one on the AP exam. It's not moving. The acceleration is positive, pushing it to the right, which means it's about to start speeding up. I guess technically you could say it's speeding up, but I won't ask you one like this, and they wouldn't ask you on the AP exam either. They're going to ask you ones like these right here, where you compare the signs, positive or negative, for velocity and acceleration. So this one, let's see, velocity is positive, acceleration is positive. They both have the same sign, and so here the object is definitely speeding up. Okay, so that's how you determine whether an object is speeding up, slowing down, or neither. Neither is only going to be when acceleration is 0. If velocity and acceleration have the same sign, whether they both be positive or both be negative, then the object's speeding up, like here and here. And if they have opposite signs, one positive and one negative, then the object is slowing down. Okay, so this is a practice problem if you want to stop and try this one. It starts off like the ones that we did in the previous lesson. I'm going to work them out, but like I said, you may want to pause them and try them first. Okay, so displacement during the first 2 seconds. You want the displacement from t equals 0 to t equals 2. Remember that displacement is final position, where it is when it ends, minus where it is when it begins. So it's the position at 2 minus the position at 0. All right, so I'm going to put these up here. The position at 0, if you plug 0 in up here, you're going to get 3. The position at 2 is going to be 8, minus 4 times 4 is 16, plus 4 times 2, 8, plus 3. So I think that's also going to be 3. Let's see, 8 minus 16 is negative 8, plus 8 is 0, plus 3, yeah, it's also 3. And so this one is 3 minus 3, or 0 meters. It doesn't mean that the object didn't move, it just means that after 2 seconds it's back where it started. Okay, so if the displacement is 0, and you're trying to find the average velocity, remember that's just the slope, it's the position at 2 minus the position at 0 over 2 minus 0. Displacement, which we already know is 0, over change in time, which is 2 seconds. And so this would be equal to 0, and if we had to put units, it would be meters per second. But instantaneous velocity requires us to find the velocity function or the derivative of the position. Okay, so I take the derivative of the position, I get 3t squared minus 8t plus 4, and I need the velocity at 2. t equals 2. So I plug it in here and I get 3 times 2 squared minus 8 times 2 plus 4, which is 12 minus 16 plus 4, which is also 0 meters per second. Usually instantaneous and average velocity don't give you the same result, but in this case we got the same thing. Okay, so again, if you want to stop the video and try these, I'm just going to go ahead and work them out. Okay, particle is at rest when the velocity equals 0. So we need to figure out, when does the velocity equal 0? Well, if I go back to the previous screen, the velocity is 3t squared minus 8t plus 4, and I need to know, when does this equal 0? Okay, so we'll solve this by factoring. That factors into 3t minus 2 and t minus 2. Let me just double check. On the outside we get negative 6, on the inside we get negative 2. Yep, that's right. Okay, and so this will be at t equals 2/3, and again at t equals 2. Now I should have already known it was going to happen at t equals 2, because back here on the previous slide, when I tried to find the velocity at 2, I got 0 meters per second. Now I'm trying to figure out, when is the particle at rest, or when is the velocity equal to 0? Well, that happens at 2, but it also happens at 2/3. Okay, now the new part that we did in today's lesson is finding the particle's acceleration, which way it's moving and speeding up, slowing down, or neither. Okay, so the acceleration, first I need to find the acceleration function, which is the derivative of velocity, or the second derivative of position. So that's going to be 6t minus 8. And if I want to know the acceleration at t equals 1, I just plug it in here and I get 6 minus 8, or negative 2. And this would be in meters per second squared. Okay, which direction is the particle moving at t equals 1/2? Well, the direction an object's moving relies on the velocity. So I need to know, what is the velocity at t equals 1/2? So I need 3 times 1/2 squared minus 8 times 1/2 plus 4. Okay, now here's an interesting thing. I really don't have to get an exact answer. I just need to figure out if this velocity at t equals 1/2 is positive or negative. Okay, well, this first part is going to be 3 times 1/4. 1/2 squared is 1/4, so 3 times 1/4 is 3/4, minus 8 times 1/2, or 4, and then plus 4. Okay, so this one's easy enough to figure out. It is just 3/4, but really all I need to know is if it's positive, if the velocity is positive or negative at t equals 1/2. So I would say that the object is moving to the right, and if I had to give a justification, which be prepared to do that, it is because the velocity at 1/2 is positive. Okay, now I need to know if the object's speeding up, slowing down, or neither at t equals 1/2. Well, in order to do that, I have to find the acceleration at 1/2. I already know, let's see if I can highlight it here. I already know that the velocity at 1/2 is 3/4, which is positive. Now I need to find the acceleration at 1/2. If it's also positive, then the object's speeding up because they'll have the same sign. If it's negative, the object's slowing down because they have opposite signs. Okay, so let's figure out the acceleration at 1/2. Okay, here's my acceleration formula, 6t minus 8. So 6 times 1/2 minus 8 is 3 minus 8, or negative 5. Okay, and so this happens to be negative. The acceleration at 1/2 is negative. Okay, so since velocity is positive at 1/2, but acceleration is negative, I would say that the object is slowing down. And if I had to justify, which you need to be prepared to be able to do, slowing down because velocity at 1/2, v of 1/2, and a of 1/2 have opposite signs. I don't have to say which one's positive, which one's negative. I've already shown work. We can look up here and see that. Right now in my justification, I just have to say it's because they have opposite signs.